In this section, we're going to be looking at empirical probability. And before we get into that too much, we need to get through some definitions. So these definitions are just going to help us be able to talk about what we're observing in our probability questions. So the first definition is an experiment, and we're told that experiments are activities in which specific results can occur. We're going to come back and look at examples of each of these definitions in a second. Outcomes are the most basic possible results of observations or experiments. So it's what we might observe happening when we perform an experiment. An event consists of one or more outcomes that share a property of interest. The sample space is the set of all possible outcomes in an experiment. And then in general, a probability is a measure of the chances or the likelihood of a particular event occurring. And so we're going to consider an experiment where each student rolls a single six-sided die. So we have just a standard six-sided cube die. Each side is labeled with either 1 dot or 2 dots or 3, 4, 5, or 6. And so if we go back up here, we can consider our experiment to be rolling a die. The outcomes then, so the possible results from rolling a die would be we could either roll a 1, a 2, a 3, 4, a 5, or a 6. So each of those would be outcomes. An event. So an event, as said, consists of one or more outcomes that share a property of interest. So maybe we have an event that is rolling an even number. Then the outcomes that would be in the event of rolling an even number would be 2, 4, and 6. So that's one example. The sample space is going to be the set of all possible outcomes in an experiment. Usually we're going to list those out using set notation. If you take a look down here, this example asks us to do that. So it says when rolling a six-sided die one time, what is the sample space? So we're usually going to use a capital S to represent our sample space. We will put inside curly brackets the list of each possible outcome. So we could get a 1, 2, 3, 4, a 5, or a 6. And so those would be the 6 outcomes that make up our sample space. Okay, and then once we have those outcomes, we can start finding probabilities, which are chances or likelihoods of either events or outcomes. I guess what I want to start with is assuming that we could actually do some data gathering together or some data collection together, but I have some data collected in previous classes. And so we're going to use that data, and it says as a class we rolled the die 500 times and observed a 5 87 times. And we're asked to find the probability of rolling a 5 using this class data set. So in general, the probability of a specific event, in this case rolling a 5, is going to be the number of ways the event can occur divided by the total number of possible outcomes, okay, or the total number of trials, okay. So in this case, that's the rule that we're going to use for probability once we get to what's called theoretical probability, where we're not actually performing an experiment, we're just using theory. In our case, what we're going to do is we're going to find the empirical probability. And the empirical probability is going to come from an experiment, so actually performing the experiment and observing what happens. So I always remember that because empirical and experiment both start with E, and in both of those cases, those go together. So when we're finding a probability or estimating a probability using an experiment, that's an empirical probability. So when we roll a 5, we observed 87 5s. We rolled the die 500 times. And so to estimate the probability of rolling a 5, we would take the number of 5s that we got out of the total number of dice rolls. And so that's 87 out of 500, which is about 0.174. Okay, so that would be our estimate for the probability of rolling a 5. And again, that is an empirical probability. Okay. Empirical probabilities are useful, particularly in statistics when you have no theoretical basis for trying to determine a probability, or if we want to try and check the validity of probabilities calculated theoretically. In the next few chapters, we're going to move on to theoretical probability. So I want to go into a little bit more detail about this die experiment of rolling the die. So what I have for us here is going to be a cumulative frequency table for our dice rolling experiment. So when we first started out, I rolled one die myself. And when I rolled the die, I did not get a 5. So at that point, when I had only rolled the die once, I did not get a 5, so the number of 5s was 0. And our estimate of the cumulative relative frequency here was 0 out of 1, or 0. Okay. We continued to roll the die a few more times, and by the time we were up to 10 dice rolls, we actually had observed 2 5s. And so the cumulative relative frequency at that point was 2 out of 10, which is 0.2. We continued rolling, and by the time we were up to a total of 60 rolls, we had 9 5s, giving us 9 out of 60, which is a cumulative relative frequency of 0.15. By the time we were at 150, we had rolled 27 5s, which is a cumulative relative frequency of 0.18. And then I didn't write down any other data until we got all the way up to 500. And at 500, we had 87 5s. And 87 out of 500 gives us 0.174, which is the 0.174 we saw up here. Okay. And so there's something important that you can see nicely happening here, and that's what I want us to talk about on the next page. What we're asked to do here on the next page is to make a line graph plotting the total number of rolls along the horizontal axis and the cumulative relative frequency along the vertical axis. So we're going to do that here. So this is number of rolls, and this is cumulative relative frequency. Okay, and so we have, let's see, that's about 100, 200, 300, 400, 500. And our cumulative relative frequencies, our smallest one was 0, our largest one happened to be 0.2. So I'm going to do 0.05, 0.10, 0.15, and 0.20. Okay. But so what I want us to see happening here is when we had only rolled the die one time, so we're almost right on the vertical axis. We're here right at 1 roll. Our estimate for the probability of rolling a 5 was 0. And that's because we had rolled a die 1 time and we observed 0 5s, and so our estimate at that point was 0. By the time we rolled the die 10 times, so now we're about here, that probability had jumped up to 0.2. And then as we keep going here, by the time our number of die rolls was at about 60, so now we're about here, we had 9 5s, so we were at about 0.15. And by the time we had a total dice rolls of 150, we were at about 0.18. And then as we got out to 500s, way out here at 500, we had moved to about 0.174. And because I didn't write down any other data in between there, we don't really know what's happening there. But the key idea here that I want us to notice is what's happening with this line graph. So as you can see at the beginning, when you have a very small number of observations, so you haven't repeated the experiment very many times, you're going to get these large swings in your expected empirical probability, or in those cumulative relative frequencies. And then what happens is, as your number of trials starts to get larger and larger, what happens is that empirical probability is going to kind of settle into the actual true theoretical probability. And so what you're seeing happen here in both the table that we looked at and in this graph is the idea of what's called the law of large numbers, which tells us as the number of trials, n, increases, the relative frequency tends towards the actual probability. So if we look, by the way, at the actual probability of rolling a 5 on a single die, we can do this. Basically, this is asking us to find the theoretical probability. Of rolling a 5 on a single dice roll. Well, there is one way to get a 5, and that's if we actually roll a 5 out of 6 possible outcomes, right? 1, 2, 3, 4, 5, or 6, which if we take a look here, 1 out of 6 gives us 0.166 repeating. Okay, and what you can see if you look above at the graph that we were drawing is 0.166 repeating is about here. I wish I had a ruler, but I don't, so we'll just do this, right? And there's that 0.166 repeating, which is the actual theoretical probability of rolling a 5. And what you can see is as your sample size increases, right, as n increases, your number of trials, that relative frequency starts to get closer and closer to that true theoretical probability. And by the time we were out to 500 rolls, we were actually getting pretty close to the true value there, okay?